Hello everyone and wish you a very warm welcome to this course on implementing PWM strategies using the Texas Instruments TMS320F28379D microcontroller. So in this lecture, I'm going to give you an overview of what this course is all about and what you can expect from this course. So this course will describe how to generate gating signals according to various PWM strategies that are implemented for different power converters. Now in this case, of course, I'm going to talk about the more generally used PWM strategies and for the more popularly used power converters. There are certain specialized PWM strategies and also certain specialized power converters which will not be covered in this course. This course will use the Launch XL F28379D evaluation kit with the Texas Instruments TMS320 F28379D microcontroller. So again, details of this can be found in my basic course on programming the TMS320F28379D microcontroller, which can be found in the description of this course and will also be described in the next lectures on the requirements of this course. So what is the objective of this course? The objective of this course is to describe how a power electronics engineer can translate simulations performed using a simulation software such as QSpice into control code for a practical microcontroller. And one of the reasons why I wanted to create such a course is because you have a lot of simulation courses and you have a lot of videos on simulations which you can find on various media such as YouTube and many others. However, for most power electronics engineers, the major stumbling block is practical implementation on a microcontroller for a hardware setup. And therefore, in this course, I hope to start exploring this particular domain where it will describe how, given a particular simulation, and if we do have such a simulation, and in this case, I'll be using simulations with QSpice once again from a previous course which I have created on PWM strategies with QSpice. And in this case, I'm going to show you how you can translate those simulations, or rather you can translate the control code in those simulations into control code for a microcontroller. So this course will be ideal for power electronics engineers who are beginning with their hardware projects. So that is, if you are a power electronics engineer who is familiar with some theory, who's done some simulations, who is now ready to start building hardware, then in that case, this course will be a very good course on getting familiar with different strategies which are there for generating gate pulses for these converters. So now I will give you an overview of everything that we will cover in this particular course. So this course will begin with the simplest power converter, and that is the buck converter. The reason why it is simple is it has a single power module, and this single power module is simply controlled using a comparison between a sawtooth carrier waveform and a duty ratio. Once this is done, now I will start examining how you can generate gating pulses when you have converters with multiple devices. Now to begin with, I will start with converters with two devices. Now here too there are various ways in which you can have two devices. I will start with a power converter which is a modified buck boost converter that has two devices. But these two devices are two different discrete power devices, but they still need to be coordinated. Once this is presented, I am now going to talk about the half bridge module. And the half bridge module now consists of two power devices connected in series. And if you take my previous course on PWM strategies for power converters, you will find that these kind of bridge modules are becoming very popular because they are available as a single module, which means you have multiple power devices connected together in a single module, and this module not only has the power devices but it also has auxiliary circuits such as gate driver circuits, protection circuits and many others. So once we have now covered the half bridge module, we will now cover the full bridge module, and the full bridge module now is two half bridge modules connected in parallel, which means now you have four power devices in a single module and in a single converter. So this means now you have a greater degree of freedom in generating the gating pulses, and also things can get a little more complicated. And eventually we will look at PWM strategies for three-phase converters. And these three-phase converters consist of three half bridge modules connected in parallel. So there is one half bridge module for each phase. And in this case, I'm going to talk about the two most popular strategies, which is one is the carrier based sine triangle modulation strategy and the space vector modulation strategy. So in this course, as I said, this is one of my first experimental courses where I'll be bringing in two different types of content together. So I'll be presenting QSpice simulations of power converters along with their control code. And I will also be looking at microcontroller programming with the F28370. So therefore, there's going to be a lot of jumping back and forth. I'm going to look at the QSpice simulation, the control code, and I'm going to then describe how with this control code, you can now write the control code in a microcontroller. Now, the reason why I want to do again is I want to describe how you can use this approach in translating a simulation into a hardware implementation. Now, the good part is some of the control, at least in QSpice, you can write your control code in C language. You can also write it in C++, you can also write it in Verilog, but in this particular case, I will use C language. So the control code in QSpice, which is in C language, and you will find this in the previous course, can be copied over directly in some aspects. All right. So in some aspects, you will need to make modifications, and I will describe where those modifications need to be made. But a lot of the code can be copied over directly. And in some cases, for hardware implementation, we do need to make some modifications, right? And this needs details of the enhanced pulse width modulation module of the F28370. This again has been described in great detail in my basic course on programming the F28370 microcontroller. Now, one of the good aspects is that in many cases, when you actually translate this simulation to hardware, you will find that the implementation in hardware is actually in some cases easier than the simulation. And the reason is that the enhanced pulse width modulation module in the F28370 offers a great deal of flexibility, a lot of features, a lot of configuration options, and these configuration options make implementation extremely easy. And I'll be describing it in this particular course. So with this, I would like to formally begin this particular course. If any of this was not clear to you or you still have any other doubts, please do post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture where I will talk about who are the target students of this particular course. Thank you so much for listening and see you soon. Goodbye for now.